Good morning, everyone. This is Optics lecture number 17, and we were discussing. We had finished Prism in the last class. I hope you remember it. Yes or no? Okay. So in today's class, we start with the next topic, and the next topic is a smaller one. And I've seen questions of this topic come, and most of the students are not able to attempt it because they have not gone through these small things, simple things. So we will start with this, and the heading is chromatic aberration. Have you heard this term, chromatic aberration, previously? I'm audible and visible, na? The setup has changed. I've come to someplace else. That is why I'm just ensuring that you can hear me and you can see me. Correct? You can see me, hear me? Okay. Chromatic aberration. Now, we have seen in the previous lecture that white light consists of 7 different colors, 7 different wavelengths, and the refractive index depends on wavelength. In fact, it is normally, if I say vaguely, it is inversely proportional to wavelength. For violet, the wavelength is smallest, and hence mu is very high. Mu is the largest. For red, wavelength is largest, and hence mu is smallest. Okay. Now, depending on the value of mu, the white ray deviates, and we have violet deviating the most, and red deviating the least. Similar thing happens even if we don't have a prism, we have a lens, and most of you might be wearing lenses, and I feel that my eyesight has gone weak, so I might be wearing lenses as well. Now, when you are wearing lenses, these lenses have a defect. Now, this defect is known as the chromatic aberration. Now, why does this defect occur? You can see in the diagram, and this diagram is given on your page number 39 in your sheet. Here you see white light incident on a lens. Remember, white light is not a single light. It consists of 7 different wavelengths. Now, when white light falls on this lens, obviously all the different colors, they have different wavelengths, so they get deviated or they get refracted differently. As you can see, the red light, remember, for red light, wavelength is largest and hence mu is smallest. It gets deflected or deviated least. So what you see is red light getting focused at a different point. But for violet light, which has the least wavelength, value of mu is largest and it gets deviated the most. The violet light is focused at a nearer point because it gets deflected more. Now this FV is known as the focal point for the violet light, and this FR is known as the focal point of the red light. If there is any light in between, for example yellow, which is the mu is between red and violet, where will the yellow light be deviated? Yellow light would be deviated somewhere in between red and violet. Do we understand this? Or make it correctly? Try it again. The yellow light would be somewhere here. Do we understand this? This defect, and why does this defect come? Because focal length of the lens, and we have seen the lens maker formula. Do we remember the lens maker formula? 1 by f is mu minus 1 by r1 minus 1 by r2. For all these wavelengths, r1 and r2 are same. The only thing that is different is mu. And hence, because of this difference, all the colors will get focused at different points. Remember, if the question comes on this chromatic aberration, they might give you a diagram, they might give you 4 diagrams and then ask you which is the correct diagram. So remember, Violet, smallest wavelength, largest mu will be deflected. The most it will be focused at the nearest point, and the red light will be focused at the farthest point. Do we understand this? Yes or no? Can I have some raised hand and we understand this? So this defect is known as chromatic aberration. How do you write it? The image of an object in white light formed by a lens is usually colored and blurred. It will be blurred. This defect of the image is called chromatic aberration, and it rises to the fact that focal length is different for different colors. I'll give you a minute to note this down. I hope everyone understands this. Please note it down. I'll give you a minute to do it. Then let's start. Now, what we have seen is violet and the red light, they get focused differently, and therefore we have focus for violet light, we have focus for red light, and similarly we have focus for blue light, green light, and so on. That takes us to the next term that we are going to understand. This is known as longitudinal or axial aberration. Term might look very complicated, but if you look at it closely, it is not so complicated. We have already understood it. What we have understood that when a white object O is situated at the axis of a lens, images of different colors are formed at different points. We have seen red light will get focused at a farther point, violet light will get focused at a nearer point. This formation of images of different colors at different positions is known as axial or longitudinal chromatic aberration. So what we have seen happening in the previous diagram, that is known as longitudinal or axial chromatic aberration. We have seen that focal length is directly proportional to wavelength. We have seen from the lens maker formula that 1 by f is equal to mu minus 1 multiplied by 1 by r1 minus 1 by r2. So 1 by f, remember these two things, 1 by f is directly proportional to mu, but mu is inversely proportional to wavelength. That brings us to the conclusion that focal length is directly proportional to wavelength. Do we understand this? Therefore, focal length for red light will be more than focal length for the violet light, and therefore you can understand it in this way. Focal length of red light is more, so red light will get focus at a farther point, whereas the violet light will get focus at a nearer point. This difference between Fr minus Fv is omega times Fy, where Fy is the focal length for the yellow light. This Fr minus Fv, which is nothing but equal to omega times Fy, is known as axial or chromatic aberration. Do we understand this? Okay, when the object is at infinity, then the longitudinal chromatic aberration is equal to the difference in focal length Fr minus Fv. Axial or chromatic aberration is nothing but equal to Fr minus Fv. Do we understand this? I'll just show you in the diagram so that it makes more sense. And here is the diagram coming for you again on the big screen. I hope you can see this diagram. You can see this. This is the focal length Fv for the violet light from here to here. Tongue, tongue, tongue. This is the focal length for the red light from here to here. Tongue, tongue, tongue. The difference between the focal length FR minus FV diagram, if you have seen it, page number 39 on your sheet. The diagram, when you see FR minus FV is equal to omega times Fy. This is what you need to understand. I hope you can understand this. And I have some reason that we have understood this. This is known as axial or longitudinal chromatic aberration. I give you a minute to note this down. The diagram should be there. If you don't want to draw the diagram in your sheet, then mark it. If you don't want to draw the diagram in your copy, then mark it on the sheet. But remember, 1 by f is directly proportional to mu. Mu is inversely proportional to wavelength. Therefore, focal length is directly proportional to wavelength. Remember this and you will be good. I'll give you a minute to note these things down. The time starts now. I hope everyone is feeling good. Do you had your breakfast and all? Note it down. I'll give you a minute. Have you noted it down, beta? Okay. Then, as I said, there are two types of chromatic aberration. One is along the axis. Violet light will get focus at a nearer point. Red light will get focus at a farther point. This is along the axis. Whenever we have something along the axis, it is normally known as longitudinal or axial. Do we understand this in optics as well as in other branches of physics? Longitudinal or axial. Now, if there's something on the longitudinal line, is along the axis, there must be something on the perpendicular line. That aberration is known as lateral chromatic aberration. Now you can see from the diagram, and I shall show you the diagram on the bigger screen, and here it comes. Now, you have an object which has some height. AB is an object which has some height. It is emitting white light. Now, as you can see, red light is getting focused at a farther point, and violet light is getting focused at a nearer point. Now, what difference does it make to the height of the object? Height of the object. Object has a height. The height is perpendicular to the axis. Height is perpendicular to the axis. What difference does it make to the height of the object? The height for the violet object, which is nearer, is smaller. The height for the red object, the image which is formed in the red color, the height is more. HR is the height of the red image. HV is the height of the violet image. And you can see this difference between the two heights, which is nothing but HR minus HV. This HR minus HV is known as lateral chromatic aberration. Do we understand this? Longitudinal is along the axis. Lateral is the difference in height. Remember, the height in the violet image will be smaller. The height in the red color would be the image. The height of the image in the red color would be more. HR minus HV is known as the lateral chromatic aberration. This is the entire thing that you have to understand. Please note it down together with the diagram so that if this question comes, I'm sure not many students will be able to solve this. So you will have an H, you will score +4 here. HR minus HV is known as lateral chromatic aberration. Do we understand this? Longitudinal along the axis, and this is lateral, which is perpendicular to the axis. Can I have some reason that we understand this? Okay, I'll give you a minute to note it down. Please note it down, and I'll be back. Well, I hope you have done this. I can see some raised hand. That's great. Now, if there is a defect, data, something is wrong. As doctors, as engineers, what are we supposed to do? You're supposed to rectify it. Yes or no? Doctors rectify human body. Engineers rectify everything else. So, if there's a defect, we need to rectify it. And that is the next heading that we are going to do. This is known as achromatism, the opposite of chromatic aberration. Now, one lens, let us forget about lens. We had seen prism. A prism, a single prism, produces deviation as well as it produces dispersion, splitting of light, and the lights get deviated. Now, if you have a combination of two prisms, then you can have deviation without dispersion or dispersion without deviation. Do we remember this results? Similarly, if you combine two lenses, you can get rid of this chromatic aberration, this phenomena of correcting this defect or not to produce this defect, where you have different lights getting focused at different points, is known as achromatism. If two or more lenses combine together in such a way that this combination produces image at the same point, violet and red, they get produced at the same point, that means violet, that means white light remains white light. This phenomena is known as chromatism, and this is the relation that you must remember. Omega upon Fy plus omega dash, omega and Fy are the values for the first lens. Omega dash and F dash Y are the values for the second lens. So you can even remember it in this way, or this way, or this way. This is the formula that you got to remember for achromatism. This is the relation between the focal length of the two lenses. F1 by F2 must be equal to omega 1 by omega 2 with a negative sign. That means if one lens is convex, the other has to be concave and all that. Do we understand this? Yes or no? Then the second thing that you have to remember is, if someone asks you, now this question may be out of the purview, it is in your course, but you might not get a question on this because you'll have to solve a numerical on this. They might ask you what is the combined focal length of this achromatic combination. You just use the formula for length. 1 by F is 1 by F1 plus 1 by F2. Combination of lengths, power of the combination is P1 plus P2. Do we remember this? Yes or no? So these are the points that you need to remember. Point number one, the relation between the two focal lengths. Point number two, what is the focal length of the combination that you have done? I will give you a minute. This might help you a lot. This is just the basics of, if someone gets into this ophthalmologist wala thing, or you have your own shop where you are producing lenses, or you actually start producing lenses and help other people. This is how you get rid of chromatic aberration. Give you a minute to note it down. we are done with lenses, we are done with mirrors, we are done with prism, we are done with problem in lenses, what are the defects in lenses. Is there anything that you want to ask me? You can ask now. I'll give you 5 minutes to go through everything that we have done so far. If you have any doubts, you can ask me. And then we will begin the last part of this particular chapter, ray optics, which is optical instruments. We'll be dealing with optical instruments. And one of these optical instruments is of much importance to doctors. The other one is probably more important for engineers. So we'll be dealing with all of those. Microscope and telescope. Give you 5 minutes. Go through what we have done till now, from prism to the defect in lenses. If you have any problems, let me know. Else, I will start into the next topic of optical instruments. So 5 minutes for quick revision. What all things you got to revise? What is a prism? Refracting angle, thin prism. What is deviation? What is dispersion? What is the formula for deviation? Dispersion of deviation of red light, violet light, yellow light, mean deviation. Then we have dispersive power. What all factor dispersive power depends on? Then we had defect in lenses, chromatic aberration, longitudinal chromatic aberration, and lateral chromatic aberration, and how you can get rid of these aberrations. I'll give you 5 minutes of time to go through this. If you have any doubts, please ask me.